Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. In the relaunch of the channel, this is going to be video 8, how greenhouse gases actually work. Now, if you've listened to any of my videos, my primary message in almost every video is this. The only way to prevent a climate disaster is to get to net zero greenhouse gases now. And I mean the only way, and I mean by now as soon as humanly possible. Now, in this video, I'm going to cover how greenhouse gases actually work. And this may be a topic that a lot of people are already familiar with, and so you could probably skip this video. But I thought it was, since I'm doing the relaunch, I thought it was important to have this sort of fundamental video in there as sort of a basic video that anybody who's not familiar with greenhouse gases could look at and basically get a better understanding of how they actually operate. And so if you already know that, that's fine. If you want to have a refresher, you might find this interesting. But let me talk about the kinds of questions we're going to address here. First, we're going to address, what are the greenhouse gases? How do those greenhouse gases impact temperature? What causes greenhouse gases? What determines the level of greenhouse gases in the atmosphere? Is the current level of greenhouse gases just part of a normal cycle? Or is it caused by human activity that is really causing temperatures to rise to unprecedented levels? And why net zero? So those are the topics we're going to cover here today. So let's begin. This is real basic. So the atmosphere basically has 5 spheres to it. And the sphere closest to the Earth is called the troposphere. And that's where we're going to talk. That's where the atmosphere that we're going to talk about today is. And when they talk about that atmosphere, they normally do it in terms of the dry components. And what it's made up of is 78% nitrogen, 21% oxygen, 0.9% argon, and basically just 0.1% everything else, and that includes greenhouse gases. Now, if you look at chart 3 up above, it shows you the composition of greenhouse gases. And I'm showing this composition basically in terms of their warming potential, not on the volume in the atmosphere. And so that would be 76% would basically be carbon dioxide. 16% would be methane, and 6% would be nitrous oxide. And then in 4, we have the chemical makeup of those particular molecules. And that's important, you'll see in the next slide as we get to it. And then the next question is water vapor. Is water vapor a greenhouse gas? And the answer to that question is yes, it is. But it's also excluded, basically, from all of the calculations that most people do. And so why is that? Well, one reason is it's highly variable by location. Obviously, over the desert, the level of greenhouse gases is significantly less than it is over the ocean, okay? And the other thing is it's not really directly impacted by human behavior. But the most important reason, and the primary reason, is its residence time in the atmosphere is only 9 days. So that, let's say there was, even for some reason that humans did cause it, and we cause water vapor levels in the atmosphere to go up dramatically. Well, in 9 days it would return back to normal. That's what they're saying. So that's why greenhouse gases are typically not included when they talk about, or water vapor, I should say, is not included when they talk about greenhouse gases. So let's now talk about how this basically works. So you have one thing is the greenhouse effect. So what happens is that the Earth is really fundamentally heated from the sun. And so the sun is very hot. It's about 5,500 degrees Celsius. And so when sunlight comes to Earth, it comes to Earth as a shortwave radiation. And it sort of just passes through our atmosphere and greenhouse gases and hits the surface of the Earth. Now, some of it gets reflected directly back into space, and that mostly happens over areas covered with snow and ice and and white kinds of surfaces called the albedo effect. But most of it gets absorbed into the Earth's surface, and that could be over land, over water, etc. And then what happens is, because the universe always seeks energy balance, okay, so what happens is then some of that heat then gets radiated back into space. Only when it gets radiated back from the Earth's surface into space, it goes back as long-wave radiation. Why? Because the Earth is much cooler. The Earth is only 15 degrees Celsius, which would be the equivalent of 59 degrees Fahrenheit. So it goes back with a different wavelength in it. Okay, now let's get to the next slide here. Now let's talk first about, very basically, about molecules. So if you can see, there's matters made up of molecules. Molecules are made up of atoms. Atoms consist of electrons and nuclei with protons, etc., and things like that. So and then from there it gets into quams and quarks and other kinds of things like that. But we're going to really concentrate on the atom portion of this. I want to show the other stuff just to give you an appreciation for how sophisticated, or how much Earth's individual molecules really are. There's a lot going on there. They're very, very, very dynamic, okay? But we're going to just concentrate on the atom portion of it, okay? Now, what happens is that the interaction within the atom has wavelengths with it. And it so happens, by coincidence, that wavelength of long-wave radiation, of radiant heat leaving the Earth and going into the atmosphere, is of the same wavelength that's going on within these greenhouse gases. And so as a result of that, what it does is it pushes some of those greenhouse the radiant heat back to Earth. It interacts with it. If you take a look at the illustration on the right, you can see sunlight coming in. Now, some of it goes back up through the atmosphere, and some of it, even as long-wave radiation, escapes greenhouse gases and just goes harmlessly into the atmosphere. But some of it is in turn captured by these greenhouse gases and redirected. And as a result of that, the temperature of Earth, for example, would be minus 18 degrees Celsius, or basically 0 degrees Fahrenheit, if we didn't have greenhouse gases. But because we have greenhouse gases, the temperature of the Earth actually rises from a minus 18 degrees Celsius to 15 degrees Celsius, which is equivalent to about 59 degrees Fahrenheit. Now, this is a fairly technical matter, and I have limited resources, but there are really some excellent illustrations out there to show you exactly how this works. And I thought I would put the QR codes up for two of them I found particularly good. So number 4 is a QR code for a YouTube video called The Greenhouse Effect by Bozeman Science. It's about less than 10 minutes long, and it's really very informative. And the other thing is the fifth source here, number 5 rather, is it's an online article from Quantum magazine. It's called The Quantum Mechanics of Greenhouse Gases. And despite the very complex titles, a very understandable illustration of how this works. And I would highly recommend you watch either, both, or one of those if you want more information about how this process actually operates. Now, let's get to Earth's surfaces. So Earth right now, as we mentioned, is sort of in the Goldilocks zone, but actually, because our greenhouse gas levels are increasing, we get to the upper level of that Goldilocks zone. And as a result of those greenhouse gases, as I mentioned on the previous slide, Earth's temperature went from a minus 18 degrees Celsius to a very pleasant 59 degrees Fahrenheit, or 15 degrees Celsius. Now, what happens if we get too much greenhouse gases in our atmosphere? And so I think we have some excellent examples in our neighboring planets, okay? Venus has a very, very, very dense atmosphere. And so as a result of that, the temperature stays pretty much the same at 867 degrees Fahrenheit. Now, Mars has a very thin atmosphere, and it's normally 70 degrees Fahrenheit during the day, but at nighttime, it's a minus 225 degrees Fahrenheit. Now, I understand Venus is also closer to the sun, and Mars is farther away from the sun than Earth is, and that has some impact on it. But most of that impact really comes from the atmospheric levels around those planets. And just one other editorial point, okay? And people are very interested in getting to Mars right now, which is terrific. I mean, I think you always learn new things by exploring, going to other planets and things like that. But sometimes people look at it and say, well, I think we're ruining Earth here. Maybe we need to figure out how to live on another planet like Mars. Well, we're not going to be able to live on Mars with those kinds of temperatures, with any kind of mass. So maybe what we need to be doing is taking some of the money we're doing that and other things and putting it to make sure that Earth stays within the Goldilocks zone. I mean, that seems to make a lot more sense to me. Just a side editorial comment, okay? So let's get to the facts here. So what's happened is this chart shows two things. It shows carbon dioxide levels, which is measured in terms of particles per million in the atmosphere, and it shows temperature. Now, what you'll see, the red is the amount of carbon dioxide particles in the atmosphere. And you can see in 1850, and for a long time, it was below 300 parts per million, and then it went just slightly above that for a while. But you can see in recent years, it has just shot up dramatically. We've gone from sort of a curved thing to almost like a logarithmic kind of move upward. And why is that? Because the amount of particles in the atmosphere have gone up dramatically. And they've gone up every single year. And you can see that from this graph here. And so we're now up to over 400, probably about, I can't remember the exact number, somewhere between 425 to 430 particles per million right now in the atmosphere. And you can see temperature just follows along. Now, the only difference is you'll notice the temperature line is wavier than the curve for carbon dioxide particles in the atmosphere. And that's because there's other things that affect temperature too. One of the big things is an oscillation called between El Nino and La Nina. So in El Nino years, you see big spikes in temperature. In La Nina years, you see them go down. That explains a lot of the upward and downward movement you see of temperatures as you look at that graph. Now, a quick question. So we know that, well, yeah, but how do we know these? How do we calculate actual temperatures? I did a whole video on that, video 4. But if you haven't watched it, I just wanted to show you this because I want you to understand how accurate those numbers are. Here we show 6 of the 7 organizations that have tracked actual temperature. And you can see they do it from 1850 on to 2025, the last time you did it. And you can see it sort of varies up and down. Now, in the early years, you can see there was some difference between them. But you can see in later years, it's just the lines almost become identical. Well, why is that? Because we have much more information now. We have satellites. We have ocean buoys that go up and down that capture temperature. We have weather, but we just have massive amounts of information. I explained all of that in video 3, okay, and also a little bit in video 4. So I'm not going to go into that now. But as a result of that, these lines have just basically converged, and these calculations are very sophisticated and are done by different organizations around the world. And to just maybe give you real quickly an illustration so you understand how sophisticated this is what the European Union does. It's called the Copernicus climate model. What they do is they basically go above the Earth's surface and they create, over the surface, they create horizontal grids. And these grids are really sort of squares. They're almost 31 by 31 kilometers, or 19 miles. And then what they do, they actually form cubes. And those cubes then are stacked 137 layers into the atmosphere. And they go up approximately 50 miles in height. When you do that, you end up with 74 million cubes of information. Now, these cubes, which you put information in, the kinds of information they put into these cubes are sort of illustrated on the upper right-hand corner here, and we talk about that in video 4. But there's more than just information about temperatures, okay? And then what they do is they calculate that temperature every single hour. They fill the cube up with information from satellites and just all kinds of things like airplanes, etc. And then every hour they empty the cube and bring in additional information. So they basically calculate average temperature 24 hours a day, 7 days a week, using 74 million cubes. Now, these cubes are also of different heights, okay? The height of the cubes near the Earth's surface are about 10 meters, and then they gradually go up as you get higher into the atmosphere. Why? Because there's a lot of variability at the surface of the Earth, because you have oceans and deserts, and mountains and valleys. But as you get up into the stratosphere, not the this actually does get in the stratosphere, but as you get up higher into the atmosphere, there is less variability that occurs, and so the cubes get higher to reduce mathematical calculation problems of supercomputers. But that's how we calculate actual temperature. I just want to show you those two graphs so you understand when you see a temperature number here, how accurate that number is. Now let's move back to talking about the other greenhouse gases. In this we show 4 charts. The first one in the upper left-hand corner is temperature, and then in the upper right-hand corner you see carbon dioxide particles. That sort of consists of what we saw before. And what do you see? They sort of move in lockstep, right? Now, in the lower left-hand corner, we have methane. Now, we didn't start tracking methane to 1927, and so as a result, this isn't much history, but you can look at the graph. It looks exactly like the other ones, right? It goes from the lower left to the upper right, right? And now the same thing's true for nitrous oxide. We didn't start tracking that to the 1990s, I think, or somewhere around there. And what do you see? The same kind of thing. It goes from the lower left to the upper right. They all look identical, okay? So whether you're talking about carbon dioxide or methane or what other kinds of things, because we have history going back 800,000 years for carbon dioxide, but we don't have it for these other greenhouse gases. But I want you to know the patterns are all identical. Now, we talked about this a little bit earlier, so I want to just spend a second before we get to the next table. Because when we talk about greenhouse gases in this chart, we're talking about the global warming potential, or GWP, over a 100-year time frame. So it's not the volume, it's the warming potential. And if you take a look at that, we can see in that case, 76% of the greenhouse warming potential is carbon dioxide, 16% is methane, 6% is nitrous oxide, so that really represents most of it. It's 98%, okay? So let's move on. Now, this is a very complex, but a very, very, very important chart. So let me walk through the columns first, and then we'll talk about the rows. So the first column is the type of gases. We use the big 3 for greenhouse gases. What are the sources of those gases? What is the volume of those gases in the atmosphere when you look at it in terms of volume? What's the atmospheric life of those greenhouse gases? What's their warming potential over a 100-year period? And then what is the GWP 100? That means what is the real warming potential then of these greenhouse gases when you take all of that into consideration? So let's start with carbon dioxide for how this works. That's the second row down. So carbon dioxide, where does it come from? It comes from fossil fuels, deforestation, transportation, producing things like steel, plastic, cement, etc. From a volume perspective, it represents 99.4% of the greenhouse gases, almost all, okay? Now, what's the atmospheric life? So when we emit CO2, the Goldilocks sort of immediately sort of redistributes it. So 25% roughly goes gets absorbed into the ocean. 25% gets absorbed by terrestrial life. That would be like plants and soil and things like that, human beings. And then the other 50% sort of stays in the atmosphere. The half that stays in the atmosphere, though, is not chemically destroyed. So it just accumulates and sort of thickens like a thermal blanket, trapping heat in the atmosphere. It does have an exit. It does eventually leave the atmosphere, but it's a very slow process. So for the 50% that's up there, it could take hundreds to thousands of years for that to get done. And eventually will get put to the ocean, sink to the bottom of the ocean and form rocks or other kinds of things like that. So that can take a long time. It has a global warming potential of 1. Why 1? Well, because it was the largest percentage of things in the atmosphere, they just arbitrarily assigned it a value of 1. But when you take into consideration all those factors, in terms of the warming potential of the greenhouse gases, it only represents 76%. The next line is methane. How do we get methane? Well, from agricultural natural gas, landfills, permafrost thaw, etc. From a volume perspective, it only represents 0.4%. But methane has a good thing about it. It has a shorter lifespan in that what happens is that it eventually will break down. It will break down basically over a period between 7 to 12 years. So that's good. The bad thing about it is that it has a warming potential of 28. So it has 28 times the warming potential of carbon dioxide. And as a result of it, this 0.4% turns into having a warming potential then in the atmosphere of 16%. Now, the one good thing about methane is that if we were able to eliminate methane getting into the atmosphere, that impact, that 16% impact, would flush away in about 7 to 12 years. So that's a very positive sign with methane. The next one is nitrous oxide. Where does that come from? Well, from fertilizer, biomass, combustion, industrial processes, and things. It only represents 7/100ths, I should say, of 1%. A very small number. But nitrous oxide is the most stable of the reactive greenhouse gases. It basically remains in the atmosphere about 100 years before it eventually breaks down. Now it has, though, a warming potential of 265. So it's 265 more potent than carbon dioxide. And as a result of that, from a warming potential standpoint, this 7/100ths of 1% really represents a 6% of the warming power of greenhouse gases in the atmosphere. This is a category we need to pay great attention to because it stays in the atmosphere for 100 years or more, and it has a warming potential of 265. Now, let's talk about one other thing in carbon dioxide. And here I used a graph that was available through 2021 as opposed to 2025 because it had a yellow line. It was easier to see. And so if you take a look at that graph, now on the left-hand side, take a look at the graph in the upper right-hand corner. It shows population growth. And, I graduated from high school in 1960, so there were about 3 billion people on Earth then. In 2025, we hit over 8 billion people. That's 5 billion more people are on Earth during my lifetime. Now, if you take a look at that graph, it looks a lot like the carbon dioxide graph and the temperature graph, right? So I think that means there is an influence here. But let's also take a look at the graph, and you see that we're projected to go up close to 10 billion, probably 9, 8 or something like that, in 2050, somewhere in that name. So that means we're going to have, if you look at it on a per person basis, the amount of greenhouse gases we're generating, we're going to have a significant reduction in per person greenhouse gases just to stay even with where we're at today. If we don't, that's going to continue to go up dramatically again. Now, I understand this isn't a perfect correlation, okay, and that population growth is occurring in some countries that haven't generated as much greenhouse gases as the United States and China and the big industrial areas have. But it is a factor. And I think it probably tells us an important message, because I think people think, well, this greenhouse gases are going up. I got to make dramatic changes in my lifestyle. But what we really have on a per person basis, probably, I mean, I don't have facts to back this up. I'm just guessing, okay? But I suspect on a per person basis, we probably haven't gone up much. Maybe we've even gone down a little bit. So to ignore greenhouse population growth in the greenhouse gas discussion, I just don't think is appropriate. And I just want to show that correlation here, I guess, because we have to take that into consideration also. Now, the next question that people frequently talk about, well, temperatures have been historically changing, and that is true. It says carbon dioxide levels. So we've been able to, through ice samples, have been able to track carbon dioxide levels for 800,000 years. Now, it's hard to relate to that number, so think about it this way. Jesus was born about 2,000 years ago, and we're talking about 800,000 years, okay? Now, the other thing you'll notice is that over the past, it looks like we followed some normal cycles here. There's sort of a range of under 200 to maybe up to 300, and then back down again. So we've been sort of in that range, and we seem to go through these cycles. But if you take a look of what's happened recently, we've just gone way, way, way past those cycles, and that is human-caused greenhouse gases or carbon dioxide levels in the atmosphere. And you can see it's way beyond these natural cycles. Now, what caused the natural cycles? Well, it turns out we can explain these historical cycles. These historical cycles, they normally call them the Ice Age cycles, and they're really explained by sort of three phenomena. And the person that discovered this was Milankovitch, so they're called the Milankovitch cycles. And there are three major cycles that are responsible for this historical fluctuation. And one of them is eccentricity. And this is this cycle occurs about every 100,000 years. And what it really involves is sort of the shape of the Earth's orbit. We're not a circular orbit, we're oval, and as a result of that, we're closer and further from the sun at different times, okay? And that has an impact. The other thing that happens is that what they call obliquity, and that's the tilt of the Earth. The Earth is tilted on an axis, and it changes that tilt periodically. It moves from 22.5 to 24.5, and this sort of changes the intensity of the seasons because it changes the distance we are from the sun. And that has a cycle of about 41,000 years. And then the last one is precession, which has a cycle of 23,000 years. This Earth sort of wobbles. It's sort of like a spinning top. If you spin a top, you'll notice that it will wobble. Well, the Earth does the same thing. And that affects its closeness to the sun. But when you take all three of those into consideration, those cycles, that sort of explains this historical cycle that we've seen, what they call the Ice Age cycle. And you can see clearly now we are above that. I like this chart because up above it shows where the Industrial Revolution started, and you can see how carbon dioxide levels have just shot up over historical levels since then. So let's get to one other thing. We talk about net zero, right? So what do we mean by that? What that basically means is the amount of carbon dioxide or greenhouse gases that are going into the atmosphere equal the amount that are coming out of the atmosphere. Now what happens, these greenhouse gases basically are stored in reservoirs. One of the reservoirs is the atmosphere. And there are other reservoirs on Earth. It could be sediment and things like that. It could be in living life on plants and trees on Earth, etc. Coal, gas, other kinds of items. You can see them illustrated here. And so how does greenhouse gases come out of the atmosphere? They come out through really two things. One is called diffusion. That's where it sort of settles on the surface of the ocean or land. But the primary way it comes out is through photosynthesis. And then it ends up in living things like human beings, plants, animals, etc. Those are the major reserves. I mean, that is the way carbon dioxide comes out of the atmosphere. Okay, how does it go into the atmosphere? Well, it goes into the internet through burning fossil fuels, from burning forests, volcano eruptions, decomposition of organic matter, etc. And we've got those listed here on this thing too. So it's really pretty simple. Okay, so what's important is we need to make sure what is going into the atmosphere is equal to what's coming out to get to net zero. And so that's really what we're talking about. Now let's talk about it in terms of this slide, which is what I call the bathtub effect. And so what's happening, if you take a look at greenhouse gases, and we've talked about this, is think of it as a bathtub that has a faucet and a drain. Now, over 800,000 years, the level rose some and sunk some, but basically what was coming in from the faucet and what was going out the drain were sort of equal. We were sort of staying in the same ranges. Well, what's happened in recent years is that there's been an imbalance. And so what's happening is the water level has been increasing. It's maybe actually occurred because of two things. One, the faucet has significantly increased. We've turned it on higher. And the other thing is, to some extent, the drain has probably been shrinking a little bit. If you take a look at the Amazon rainforest, all it has done, I'm recording this in August 1st of 2026. I mean, in the last 3 weeks, we have had forest fires just about every place. I mean, Canada was burning so bad, the smoke was coming all over the United States. As I speak, there's significant forest fires occurring in the western part of the United States. There's significant forest fires in Minnesota. There's significant forest fires in Europe. And all of that is shrinking the size of the drain. And to make matters worse, when they burn, they actually put more carbon dioxide and greenhouse gases into the atmosphere, so that they're actually increasing the faucet, okay? So that's what happens. So what we need to make sure is that that level doesn't get above the height of the tub, so it starts overflowing and really having a significant impact. And so when that occur, well, maybe that could occur as early as 2033 to 2040. We're not that far away from that potentially occurring, folks. That's what the scientists are telling us. And when it does, think of it if you're living below the bathtub, sleeping at night, and the bathtub is overflowing. As it overflows and more water gets in there, the conditions just get worse and worse, and eventually the whole thing is going to come crashing down, okay? So let's move on to this Titanic table. Well, you've seen this before. But when are we going to hit the iceberg? Well, if you look at this chart, I say that's sort of when we hit 2 degrees Celsius. Why is that? Because that's what the scientists tell me the world will see catastrophic and likely irreversible damage. What that means is that nature, because of its feedback loops, will probably take over increasing the level of carbon dioxide in the atmosphere. There's nothing human beings can do about it. You can see a clear example of that right now, which is what's happening with forest fires in 2026, okay? But that's just going to get worse. So that's why I say that's sort of the range when we might hit the iceberg. Based on actual temperatures, we actually increased 0.5 degrees in 9 years. If we followed that pattern, we'd be there in 2023. And then we have the client scientists say that we'll get there a little bit later. But we talked about that in some other presentations, how these models are probably way too conservative. So who knows, but we're somewhere in that range. When do we get to when does the orchestra maybe finish playing or is pretty far along in their concert? That's at 3 degrees Celsius increase, and that's what they call the nightmare scenario. And that could be in the 2050s sometimes, as early as that. So let's wrap this up. So in this video, I just want to really cover the basics of greenhouse gases. You know, you know how they're created, how they impact temperature, how the warming potential thing works, which is very important. How the Milankovitch cycles sort of explain historical changes or ice cycles that we've had on Earth. And then the really important thing is the bathtub effect. And that's why I've reached this conclusion that the only way, and I mean the only way, we can avoid a climate disaster is by getting to net zero greenhouse gases. Now, what can you do about it? Well, vote. I mean, we just need to get elected officials in there who believe greenhouse gases are an important issue and are willing to take the actions to treat that as a high priority item. And they also need to have the personality to work together with other people around the world to make that happen. The other thing is 70% of the people basically believe we have a climate crisis on our hands. But nobody's talking about it. And one of the reasons I'm doing this video is I'm trying to provide really basic core scientific information that explains really what's happening. And I've got other videos I'm going to be doing, releasing shortly, as to how we can get to net zero greenhouse gases and some of the impacts and other kinds of things. I'm only at video 8. This is right now, and so the next series of videos will really deal with how we get to net zero greenhouse gases. But share this link, talk about it with other people, and get involved. And thank you very much for your time.